In 2011, astronomers observed a colossal X-ray flare erupting from the supermassive black hole Sagittarius A at the heart of our Milky Way. This wasn't just a brief flicker, it was an extreme outburst, a million times brighter than anything seen from it before, lasting for several hours. Scientists are still puzzling over the exact cause of this unprecedented event. Was it a rogue asteroid, a gas cloud, or something far stranger being devoured? The precise mechanism behind such a violent cosmic feast remains one of the universe's great unresolved mysteries, prompting us to ask what truly happens when matter crosses the ultimate boundary. A black hole is not an empty void, but a region of spacetime where gravity is so incredibly strong that nothing, not even light itself, can escape its grasp. It forms when a truly massive star collapses at the end of its life, crushing an enormous amount of matter into an impossibly small volume. The boundary beyond which escape is impossible is known as the event horizon, often referred to as the point of no return. Once you cross this invisible threshold, your journey towards the black hole's center becomes a one-way trip. As you approach a stellar mass black hole, you would experience an extreme phenomenon known as spaghettification. Imagine the gravitational pull on your feet being immensely stronger than on your head, stretching your body like a noodle. For a black hole with the mass of several suns, the difference in gravity across even a few feet would be enough to rip you apart. Your atoms themselves would be pulled into long, thin strands, an agonizing disintegration long before reaching the core. Beyond the event horizon, the future and past switch roles, and all paths lead inevitably to the singularity at the black hole's core. Inside, space and time warp so drastically that moving forward in space becomes literally equivalent to moving forward in time. This means escaping is as impossible as reversing time itself, as every direction points you inward. There is no going back once you are committed to this one-way, space-time road. The singularity is the ultimate destination, a point of infinite density where all the mass of the black hole is theorized to be concentrated. Einstein's general relativity predicts this point, where the laws of physics as we understand them break down entirely. It's a place where space-time curvature becomes infinite, an ultimate boundary of mathematical understanding. Modern physics still grapples with what truly exists at this extreme point, or if quantum gravity might offer a different picture. Time dilation would play a dramatic role as you approach the event horizon from an external observer's perspective. You would see your clock slowing down, your movements becoming sluggish, eventually appearing frozen in time at the threshold. From your perspective, however, time would pass normally, though the outside universe would appear to speed up dramatically. You would witness the entire future of the universe unfold in a fleeting moment before your final plunge. Black holes come in different sizes, starting with stellar mass black holes, which are typically 3 to 20 times the mass of our sun. These form from the collapse of individual giant stars and are scattered throughout galaxies, often undetectable unless they are actively feeding. The X-ray binary Cygnus X1 was one of the first and most famous candidates for this type, its compact companion believed to be a stellar mass black hole. Supermassive black holes, on the other hand, are true cosmic behemoths, ranging from millions to billions of solar masses. Sagittarius A at the center of the Milky Way is one such example, weighing in at about 4 million suns. These titans reside at the hearts of most large galaxies, profoundly influencing their evolution. Their immense gravitational pull dictates the motions of stars and gas for thousands of light years around them. Then there are intermediate mass black holes, a mysterious class thought to be between 100 and 100,000 times the mass of our sun. These objects are harder to find, but evidence suggests their existence in dense star clusters. The object HLX-1, located in an external galaxy, is considered one of the strongest candidates for an intermediate mass black hole, demonstrating powerful X-ray emissions. Their formation pathways are still a subject of intense research and debate. The concept of primordial black holes suggests these could have formed in the very early universe, just moments after the Big Bang. Instead of collapsing stars, they would have been born from extreme density fluctuations in the primordial soup of matter. These hypothetical objects could range from minuscule, almost atomic sizes, to masses much larger than stars. Some theories even suggest they could constitute a significant portion of the universe's dark matter. One of the most perplexing mysteries of black holes is the information paradox, which asks what happens to the information of everything that falls in. Quantum mechanics dictates that information can never be truly destroyed, yet classical black holes seem to consume it forever. Stephen Hawking's work on black hole evaporation only deepened this conundrum, suggesting a conflict between relativity and quantum theory. This paradox remains a frontier in physics, challenging our fundamental understanding. Stephen Hawking famously theorized that black holes are not entirely black, but actually emit a faint glow of particles known as Hawking radiation. This radiation arises from quantum effects near the event horizon, meaning black holes slowly lose mass and energy over incredibly long timescales. A black hole the mass of the sun would take longer than the current age of the universe to evaporate. Ultimately, all black holes are destined to completely vanish, albeit eons from now. For spinning black holes, known as Kerr black holes, an additional region exists outside the event horizon called the ergosphere. Within this bizarre region, spacetime itself is dragged around by the rotating black hole, forcing anything inside to rotate with it. Although it's still possible to escape the ergosphere, particles entering can gain energy from the black hole's rotation. This phenomenon, known as the Penrose process, could theoretically extract energy from a black hole. Active galactic nuclei, AGN, are powered by supermassive black holes at the centers of galaxies, which voraciously consume surrounding gas and dust. As matter spirals inward, it forms an incredibly hot, bright accretion disk, emitting vast amounts of radiation across the electromagnetic spectrum. The Seyfert galaxy NGC 4151 is a classic example of an AGN, showcasing powerful X-ray and gamma-ray emissions from its feeding black hole. From these actively feeding black holes, powerful relativistic jets of plasma are often observed shooting out from their poles at nearly the speed of light. These jets can extend for hundreds of thousands of light years into intergalactic space, profoundly impacting the evolution of their host galaxies. Stunning jets from the supermassive black hole in the galaxy M87, famously imaged in 2019, are a prime example of this spectacular cosmic violence. When two black holes merge, they create some of the most powerful events in the universe, releasing enormous ripples in spacetime known as gravitational waves. The LIGO and Virgo observatories have famously detected these waves, confirming Einstein's century-old prediction and opening a new window onto the cosmos. The first detection, GW150914, marked the merger of two stellar mass black holes into a larger one, releasing more energy than all the stars in the observable universe combined. Near the event horizon, the extreme gravity causes light to bend dramatically, creating bizarre visual distortions for any infalling observer. Starlight from behind the black hole would be warped and magnified, appearing as bright rings. This phenomenon, called gravitational lensing, means you could see multiple images of the same distant objects or even see the entire sky compressed into a tiny region, a surreal and disorienting final view. The study of black holes has led to the development of black hole thermodynamics, applying concepts like temperature and entropy to these enigmatic objects. Despite their initial definition as simple, featureless entities described only by mass, charge, and spin, Hawking radiation gives them a temperature. The entropy of a black hole, remarkably, is proportional to the area of its event horizon, connecting gravity to the fundamental laws of thermodynamics in a profound way. Some speculative theories suggest that black holes might be connected to wormholes, theoretical tunnels through spacetime that could link distant regions of the universe. While mathematically possible in some solutions of general relativity, stable, traversable wormholes remain purely hypothetical. If they existed, a black hole's interior might not be a dead end, but a gateway to another universe or a far-flung corner of our own, though the physics is highly challenging. The theoretical opposite of a black hole is a white hole, a region of spacetime into which nothing can enter, but from which matter and light can escape. While black holes are supported by observational evidence, white holes are purely theoretical and have never been observed. They appear in solutions to Einstein's equations, but their physical existence is highly doubted. Some theories suggest that the singularity of a black hole could potentially connect to a white hole in another universe. Could black holes play a role in the mysterious phenomenon of dark matter, the unseen substance thought to make up about 27% of the universe's mass? While stellar mass black holes don't contribute significantly, primordial black holes could be a candidate. If they formed in sufficient numbers during the Big Bang, they would exert gravitational influence without emitting light, matching dark matter's characteristics. This hypothesis is currently being investigated with observational constraints. Scientists don't directly see black holes because they emit no light, but rather detect them through their powerful gravitational effects on surrounding matter. We observe the swirling accretion disks of gas, the extreme velocity of stars orbiting an unseen center, and the X-ray emissions from superheated material. The Event Horizon Telescope, which famously captured the first image of a black hole silhouette in M87, combined radio telescopes globally to achieve this feat. Our own Milky Way hosts the supermassive black hole Sagittarius A, located about 26,000 light-years from Earth. Although currently relatively quiet, its influence is undeniable, governing the orbits of stars in our galactic center. Observing stars like S2, which orbit Sagittarius A at incredible speeds, allows astronomers to precisely measure the black hole's mass. This proximity provides an unparalleled laboratory for studying extreme gravity. The groundbreaking image of M87*, the supermassive black hole at the center of the galaxy Messier 87, provided the first direct visual evidence of a black hole's shadow. This iconic image, captured by the Event Horizon Telescope, showed a dark central region surrounded by a bright ring of emission from superheated gas. The image offered stunning confirmation of Einstein's general relativity in the strongest gravitational fields. The ultimate fate of black holes in the far future of the universe is a slow, gradual evaporation through Hawking radiation. While this process is incredibly slow for massive black holes, eventually, after trillions upon trillions of years, even the most massive black holes will shrink and then disappear in a final burst of energy. They are not eternal but finite objects, destined to fade away as the universe expands into cold, dark emptiness. Despite incredible advancements, the true nature of the black hole's interior, especially the singularity, remains largely a mystery, a realm where known physics dissolves. Quantum gravity, a theory still under development, might one day reconcile the conflicts between general relativity and quantum mechanics, offering a unified description. But until then, the very heart of a black hole represents one of the universe's most profound and challenging enigmas. If you found yourself captivated by the strange physics within black holes, make sure to hit that like button and subscribe for more mind-bending cosmic journeys. What do you think lies beyond the singularity, if anything? Share your wildest theories in the comments below, and let's unravel the universe's greatest secrets together.